Hello there, and welcome to The Sleepless Scientist. Tonight, we embark on a quiet journey through time and space, to the very edges of our solar system and the secrets it has carried for billions of years. These stories are not told in haste, but in gentle whispers, as though the cosmos itself were leaning closer to share them with you. Imagine drifting slowly among the stars, unhurried, weightless, with nothing but the patient ticking of the universe to keep you company. Here, we will wander through ancient beginnings, fiery suns, and the curious paths of the planets, piecing together the history of our celestial neighborhood. You may discover facts you've never heard before, and perhaps feel a sense of wonder at how vast and delicate our cosmic home truly is. And just before we begin, if these calm, curious explorations help you unwind or give you a quiet way to end your day, consider liking and subscribing to the channel. It helps others find their way here too. One sleepy soul at a time, the birth of the solar system. At first glance, the solar system feels like a perfectly arranged clockwork, every planet moving in its place, but its beginning was anything but orderly. Around 4.6 billion years ago, a massive cloud of dust and gas, drifting through a quiet corner of the galaxy, began to collapse under its own gravity. The collapse was not sudden, but slow and inexorable, like sand slipping through an hourglass. As the particles pressed closer, they heated, they swirled, and they began to shape themselves into something new. From chaos, a disk was born, spinning like a potter's wheel, scattering light across the darkness. Within that disk lay the seeds of everything we know: the planets, the moons, the asteroids, and us. Imagine, for a moment, all of history still locked inside a haze of dust, waiting to unfold. That was the solar system's first breath, how the sun formed from a cloud of gas. Think about this. At the heart of that collapsing cloud, matter was crowding inward, tighter and tighter, until pressure and temperature soared. In time, a spark ignited, a nuclear fire unlike anything seen before. Hydrogen, the simplest of elements, began to fuse into helium, releasing light and warmth. That fire became our sun. The young star was turbulent, throwing out winds of charged particles, shaping its surroundings like a sculptor with invisible hands. Around it, leftover material whirled, some gathering into planets, others banished into deep space. The sun, still restless in its youth, shone with a fierceness we cannot truly picture. And yet, it was that glow, that brilliance, that set the stage for every planet to form, for every ocean to glimmer, and eventually, for every living thing to breathe. The sun, as 99.8% of all solar system mass. Here's something surprising. Almost everything in the solar system, the weight, the bulk, the substance, is the sun itself. About 99.8% of all the mass rests inside that one star. The planets, for all their beauty and diversity, are just crumbs left over, drifting companions to a giant. Jupiter, the largest planet, could hold more than 1,000 Earths, and yet compared to the sun, it is a mere pebble. The sun's gravity is what holds everything in place. It is the reason Earth circles gently every year, the reason comets return on their frozen pilgrimages, the reason moons cling to their planets. Without its dominance, there would be no order here, only fragments adrift in the dark. And so, in the grand balance of mass, we are but tiny satellites to a single shining star. Why the planets orbit in a flat disk? Let's go back to that swirling cloud, that first disk of dust and gas. Gravity pulled everything inward, but the spin of the cloud meant it flattened, like dough pressed by unseen hands. Most of the particles settled into this thin, rotating plane, circling the sun in graceful arcs. That is why, even today, the planets all follow nearly the same path, a great cosmic carousel turning around its center. It is not a coincidence, but the natural outcome of physics and motion. The flatness gave the solar system its structure, predictable, balanced, ordered. And yet, in this order, there is still variety. The tilted spin of Uranus, the eccentric journey of Pluto, the faint leanings of other worlds. They are reminders that even in cosmic harmony, a little chaos lingers. The mystery of planetary orbits. Every planet follows an invisible track, held in place by gravity, moving endlessly, yet never colliding. These orbits are not perfect circles, but gentle ellipses, stretched slightly like pearls on an oval string. The mystery lies in their precision. How could such immense bodies, formed in such violent beginnings, find such stable paths? The answer is a dance of forces, gravity pulling inward, motion pulling outward, a balance that never quite tips. Over eons, small tugs from one planet to another have shifted orbits subtly, creating patterns and resonances, like the repeating notes of a song. Jupiter, with its massive pull, has shaped the paths of countless asteroids. Neptune quietly governs the frozen Kuiper belt. Our own Earth, circling in its steady way, owes its position to countless such interactions. These orbits are history, written in motion, carved into the emptiness of space. Mercury, the closest planet to the Sun. At first glance, Mercury is a small and quiet world, a gray stone adrift in the glow of the Sun. Yet it is the closest of all planets, circling at just 36 million miles from the star that anchors us. From its surface, the Sun would appear 3 times larger than it does from Earth, filling the sky with a brilliance no human eye could endure. Mercury is scarred and cratered, a world shaped by countless impacts over billions of years, bearing the marks of time with no atmosphere thick enough to soften them. Though tiny compared to its neighbors, Mercury's journey is swift. It races around the Sun in just 88 Earth days, making a year there less than a single season for us. To look upon Mercury is to see a world both ancient and restless, locked in a perpetual chase around its master star. Why Mercury has extreme temperatures? Here's something curious. Despite being so close to the Sun, Mercury is not the hottest planet. That title belongs to Venus. The reason lies in Mercury's lack of atmosphere. With almost no blanket of gases to trap warmth, the planet is left exposed, vulnerable to extremes. During the day, the surface bakes under sunlight, rising to over 800 degrees Fahrenheit, hot enough to melt lead. But when night comes, the heat vanishes into space, and temperatures plunge to -300. It is a world of brutal contrasts, shifting from furnace to freezer in a single rotation. Imagine standing on that surface, the ground shimmering with unbearable heat, knowing that in hours it will be colder than any winter on Earth. Mercury's extremes remind us of the delicate balance our own planet maintains, a balance that allows life to flourish. The long day and night cycle of Mercury. Think about time on Mercury, and it begins to feel strange. The planet spins very slowly, taking 59 Earth days to complete a single turn, yet it also whirls quickly around the Sun. This unusual rhythm creates a day-night cycle that defies simple measure. From sunrise to the next sunrise, a Mercurian day lasts the equivalent of 176 Earth days, 2 of its short years stretched into one long day. Imagine standing on its rocky surface. The Sun rises slowly, climbs high into the sky, lingers for months, and then dips away again. Darkness follows, deep and unbroken, lasting nearly half a year in our terms. Such a cycle reshapes every sense of time. It reminds us that day and night, words so familiar on Earth, are merely reflections of motion, and that elsewhere, time can unfold in entirely different ways. Venus, Earth's toxic twin. At first, Venus might look like Earth's sibling. It is nearly the same size, with a similar composition, and it shines brilliantly in our sky, often called the morning star or evening star. But the resemblance ends at its surface. Beneath its thick veil of clouds lies a hostile world, where temperatures soar to nearly 900 degrees Fahrenheit and pressures crush with the force of being nearly a mile under Earth's oceans. The air itself is toxic, made mostly of carbon dioxide, with clouds of sulfuric acid drifting endlessly. No human, no fragile machine could survive for long there, and yet in its brightness, Venus continues to captivate us. A reminder that similarity does not guarantee safety, and that a world so close in form to ours can become something entirely alien. The runaway greenhouse effect on Venus. Let's look deeper into Venus's story. Long ago, it may have had oceans, gentle seas glimmering under a younger sun. But over time, the heat grew stronger, and water began to evaporate into the air. The thickening atmosphere trapped more and more of the sun's warmth, until the planet spiraled into what scientists call a runaway greenhouse effect. It became a furnace, its seas boiled away, its skies thick with suffocating gas. Today, Venus is a cautionary tale, showing how fragile the balance of climate can be. The same greenhouse effect, which keeps Earth comfortably warm, raged out of control on Venus, transforming it forever. When we study its atmosphere, we are not only looking into another planet's past, we are peering into a mirror of what could happen if balance were lost here at home. Why a day on Venus is longer than its year. At first glance, time seems simple. A day is how long a planet spins. A year is how long it circles its star. But on Venus, this relationship twists into something almost unbelievable. The planet rotates so slowly that it takes 243 Earth days to complete one full turn. Yet it only takes 225 days to orbit the Sun. That means a single Venusian day lasts longer than its year. Stranger still, Venus spins backwards, compared to most other planets, so the Sun appears to rise in the west and set in the east. Imagine standing there, if you could survive the heat, watching a sunrise that takes weeks to unfold, knowing you would not live to see it set. Time on Venus is stretched and inverted, reminding us that the simple rhythms of our world are not universal laws, but delicate arrangements of motion that differ from one planet to another. Earth, the only known planet with life. Think about this for a moment. Out of all the worlds we've wandered with our imagination, Mercury's battered surface, Venus's crushing skies, only Earth cradles life. Oceans shimmer across its surface, forests stretch toward sunlight, and countless creatures stir in the air, water, and soil. Its atmosphere is not too thin, not too thick, but just enough to protect us and allow breathing. Its distance from the Sun is neither too close nor too far, keeping water liquid, the key to life as we know it. To gaze at Earth from afar, perhaps from the vantage of space, is to see a blue jewel unlike any other we've yet discovered. And yet, even here, life was not guaranteed. It is the fragile result of billions of years of change, accident, and chance. Earth is not merely a planet, it is a rare and precious oasis in the dark. Earth's protective magnetic field. Here's something easy to forget because we cannot see it. Surrounding Earth is an invisible shield, a magnetic field generated by molten iron churning in the planet's core. This field stretches far into space, deflecting streams of charged particles rushing from the Sun. Without it, solar winds would strip away our atmosphere, as they once did on Mars. The magnetic field also paints the sky with auroras, when charged particles slip along its lines and ignite the upper air in curtains of green, purple, and red. Every breath we take, every ocean wave, every mountain, all are protected by this silent guardian. We live under its watch without noticing, as if wrapped in a cloak that never tears. The field whispers to us only when it lights the night sky, reminding us of its quiet, endless duty, the importance of Earth's atmosphere. Let's pause to breathe. Each breath we take is part of Earth's gift. Its atmosphere, a fragile envelope of gases that surrounds the world. It is mostly nitrogen, with enough oxygen to sustain us, and traces of other elements that shape climate and life. This thin layer holds warmth, shielding us from deadly cold. It scatters sunlight into the blue sky we know, and filters harmful rays that would burn the ground sterile. At night, it glows faintly with air glow, a quiet reminder that even the dark is not empty. The atmosphere carries storms, rain, and winds that nourish ecosystems and carve landscapes. Without it, Earth would be as barren as the moon. Yet for all its power, the atmosphere is astonishingly delicate, no thicker in proportion than the skin of an apple. It is both our protector and our breath itself. The moon, Earth's only natural satellite. Now, let's lift our eyes to the companion that has followed Earth for billions of years. The moon, pale and watchful, circles us faithfully, shaping tides and marking time. Its surface is scarred with craters, silent records of impacts long past. Unlike Earth, it has no thick atmosphere, no flowing water, no forests, and yet its presence is deeply felt. The moon steadies Earth's tilt, preventing wild swings of climate that could have made life less stable. It draws the oceans, lifting them into tides that pulse like a heartbeat around the globe. For early humans, it was a guide, a calendar, a lantern in the night sky. Even today, we look to it with wonder, seeing not only a celestial body, but a symbol of companionship, of cycles, of the quiet passage of time. Theories of how the moon formed. At first glance, the moon feels eternal, as though it has always been a companion to Earth. But the truth of its origin is a puzzle scientists have worked to piece together. The leading idea is known as the giant impact hypothesis. In the solar system's youth, Earth was still forming, a fiery molten world. Then, a Mars-sized body, scientists call it Theia, collided with Earth in a catastrophic impact. The collision was violent enough to throw vast amounts of rock and molten material into orbit. Over time, that debris circled, clumped, and slowly gathered into a single body, the Moon. Other theories suggest the Moon might once have been a wandering object captured by Earth's gravity, or that it formed alongside Earth in the same disk of material. But the chemistry of lunar rocks, brought back by Apollo astronauts, seems to whisper most clearly of that ancient collision. To think that our familiar Moon may be the remnant of such violence, yet now appears so calm, is a reminder of how chaos can give rise to beauty. The Moon's role in tides. Think of the ocean. Its endless rise and fall, its rhythm of waves upon the shore, is not simply the work of winds or storms. It is the pull of the Moon. Gravity reaches across space, tugging at Earth's waters, drawing them toward the Moon's position. As Earth turns, these bulges of water travel around the globe, creating the tides. They are more than just a curiosity. They shape coastlines, nurture life in tidal pools, and regulate ecosystems. In ancient times, sailors timed their journeys to the rhythm of these tides. Farmers planted by their cycles. The Moon's gentle pull may even have played a role in the origins of life, stirring the shallows where chemistry first awakened. Each wave that laps against the shore is a reminder of that silent partner above, a celestial hand guiding the oceans with steady patience. Mars, the red planet. Now let us drift outward, past Earth, past the belt of rocky asteroids, to a world that has long captured our imagination, Mars. To the naked eye, it glows like a reddish ember in the night sky, a world that feels both close and distant. Mars is smaller than Earth, with air so thin that standing there would feel like being on the summit of the highest mountain, only harsher. Dust storms can sweep across the planet, sometimes engulfing it entirely in a rust-colored haze. Its surface is marked by vast plains, craters, and mountains that dwarf any on Earth. For centuries, Mars has stirred human curiosity. Were there canals? Could there be life hiding beneath its surface? Even now, robotic explorers roam its soil, searching for clues in rocks, dust, and ice. Mars is a world both alien and strangely familiar, inviting us to dream of footsteps in its sand. Why Mars appears red? Here's something simple yet fascinating. The redness of Mars comes from rust. Its surface is covered in iron-rich rocks and dust that have oxidized over time, creating that familiar rusty hue. It is as though the entire planet is a vast desert of iron turned to powder, spread thinly across its surface and lofted into the air by winds. From a telescope, the color is striking, a warm glow against the black of space. To early observers, it evoked fire, blood, even war, which is how Mars took its name from the Roman god of battle. But beneath this dramatic tint lies a quieter truth, chemistry, working slowly over eons, transforming iron into oxide, painting a planet red. The color we see is not a mask, but the story of its rocks, its air, and its history told in light. The largest volcano in the solar system, Olympus Mons. On Mars lies a mountain so vast, it defies comparison. Olympus Mons rises over 13 miles high, 3 times taller than Mount Everest. Its base is so broad that if you stood on one side, the curvature of Mars itself would hide the other. It is not just a mountain, but a shield volcano, formed from countless eruptions over millions of years, spilling lava that spread wide instead of high, layer upon layer, until the giant was born. The thin Martian crust and lack of plate tectonics meant the hotspot beneath Olympus Mons could build upward without being shifted aside, creating this colossal structure. Imagine standing near its base, the slope so gentle you might not realize you were climbing a volcano at all, and yet you would be walking across a feature larger than entire countries. It is a monument to planetary forces, frozen in time. Mars's canyons and valleys. At first glance, Mars looks dry and desolate, but carved into its surface are scars of astonishing scale. The most famous is Valles Marineris, a canyon system so vast it makes the Grand Canyon look like a shallow crack in stone, stretching more than 2,500 miles long and up to 7 miles deep. It would span the entire United States if placed across our world. Scientists believe these canyons formed as the Martian crust stretched and cracked, perhaps when nearby volcanic regions swelled upward. Over time, landslides, winds, and maybe even water deep in its past widened the fractures into immense valleys. Imagine standing at its edge, cliffs rising beyond sight, the horizon vanishing into a haze of red, silence pressing in from all directions. On Earth, canyons echo with rivers and life. On Mars, they echo only with the memory of what once might have been. These valleys are monuments to a world that was once alive with geological change, and perhaps water flowing far below the surface. Evidence of water on Mars. Think about the role water plays on Earth. It sculpts mountains, nourishes forests, and sustains every living thing. On Mars, signs of ancient water whisper from its rocks and landscapes. Dry riverbeds snake across the terrain, gullies carved into slopes, and minerals form that can only exist in liquid water's presence. Orbiting spacecraft have captured images of dark streaks that seem to grow and fade with the seasons, possibly traces of briny water seeping near the surface. Polar caps gleam at each end of the planet, made of frozen carbon dioxide layered with ice. And deep underground, radar hints at hidden reservoirs of liquid water, locked away beneath the crust. Billions of years ago, Mars may have been a blue world, with lakes and perhaps even oceans rippling beneath a thicker sky. To look for water on Mars is to look for life's possibility. For if water once flowed freely, could something, however small, have lived there too? Jupiter, the largest planet. Now let us drift outward, beyond the belt of asteroids, where a giant waits. Jupiter, the king of planets, is a world so massive it could swallow all the others and still have room to spare. 11 Earths could line up across its diameter, and more than 1,300 Earths could fit inside its volume. Its stripes of clouds swirl endlessly, bands of gas in constant motion, sculpted by winds faster than any storm on Earth. Lightning crackles through its storms with a power beyond imagination. Jupiter is not a solid world like ours. It is mostly hydrogen and helium, more akin to a star than a planet. At its heart may lie a dense core, wrapped in layers of liquid metallic hydrogen that conduct electricity and fuel its mighty magnetic field. To orbit Jupiter is to circle a restless titan, a guardian and a destroyer, shaping the solar system with its gravity, the size of Jupiter's great red spot. Here's something astonishing. On Jupiter's face lies a storm so immense that 3 Earths could fit inside it. This is the Great Red Spot, a swirling hurricane of gas that has raged for at least 350 years, perhaps much longer. No one alive has seen it begin, and perhaps no one will see it end. Winds there roar at over 400 miles per hour, circling endlessly within an oval of rust and cream. Though the storm has shrunk in recent decades, it remains one of the solar system's grandest spectacles. From a spacecraft window, the view would be otherworldly, an ocean of clouds beneath, with a vast whirlpool the size of a planet, turning slowly, endlessly. The red spot is not just a storm, it is a reminder of Jupiter's scale, where weather itself grows into monuments larger than our entire world. Jupiter's powerful magnetic field. Let's look beyond what we see, into the invisible. Jupiter generates the strongest magnetic field of any planet, a force so vast it stretches millions of miles into space, creating a magnetosphere that dwarfs even the Sun. This field traps particles and radiation, forming belts so intense that any spacecraft daring to linger there must shield itself carefully. Within this invisible storm, auroras dance at Jupiter's poles, brighter and more powerful than any seen on Earth. They are fueled not just by the Sun, but by Jupiter's own rotation and volcanic material flung outward from its moon Io. If we could stand near those poles, though of course no human could survive the radiation, we would see curtains of light blazing constantly, never fading, never resting. This immense magnetic shield protects Jupiter's many moons, but it also makes the region around the planet one of the most hostile in the solar system. Jupiter is not only massive in size, but in influence, shaping everything within its reach. The many moons of Jupiter. At first glance, Jupiter itself seems enough to inspire awe, but then you learn it is surrounded by a retinue of moons, so numerous that it resembles a miniature solar system. Over 90 have been confirmed, ranging from tiny fragments of rock to worlds larger than our own moon. Galileo was the first to glimpse 4 of them through his small telescope in 1610. Io, Europa, Ganymede, and Callisto. And those discoveries transformed our understanding of the cosmos. No longer could Earth claim to be the only world, orbited by companions. Today, those Galilean moons still command attention, each unique, each carrying secrets of ice, fire, or oceans beneath the surface. The smaller moons, too, whisper of captured asteroids or shattered fragments from collisions long past. Around Jupiter, orbits are crowded and complex, a testament to the planet's immense gravity, which gathers wanderers into its embrace. Imagine standing on one of these moons, looking up at a sky dominated not by a sun, but by Jupiter itself, striped and enormous, filling the heavens. Europa, the ocean moon of Jupiter. Think about this. Beneath Europa's cracked, gleaming surface of ice may lie a global ocean, larger than all the seas of Earth combined. The ice stretches for miles in thickness, etched with dark lines where it has shifted and fractured. But below, tidal forces from Jupiter's gravity churn the moon's interior, keeping water liquid despite the cold. In that hidden ocean, warmth and chemical reactions may create conditions where life could exist. Perhaps strange creatures swim in darkness, sustained by vents on the ocean floor, as they are in Earth's deepest seas. We cannot yet know, but every probe that has flown by has strengthened the case. Europa is one of the most promising places to search for life beyond Earth. To look at its pale, streaked face is to wonder if we are staring at the shell of another living world, a world that whispers softly beneath its icy veil. Ganymede, the largest moon in the solar system. Here's something remarkable. Ganymede, another of Jupiter's moons, is not just large, it is the largest moon in the entire solar system, even bigger than the planet Mercury. Its surface is a tapestry of grooved terrain, bright ice, and dark ancient regions, evidence of geological activity long ago. Like Europa, Ganymede is thought to hold an ocean beneath its icy shell, making it another candidate in the search for life. But what sets Ganymede apart is its magnetic field, the only moon known to generate one. This invisible shield, born of a metallic core, interacts with Jupiter's immense magnetosphere, creating glowing auroras that dance across its surface. Imagine standing there, in a place both familiar and alien, seeing lights shimmer overhead that are not caused by the sun alone but by the magnetic embrace of an entire giant planet. Ganymede is not simply a moon, it is a world in its own right, carrying mysteries we have only just begun to explore. Saturn, the planet with rings. Let us drift farther outward, into the realm of Saturn. If Jupiter is the giant, Saturn is the jewel. Its rings make it the most instantly recognizable of all the planets, a vision of elegance suspended in the dark. The planet itself is a pale golden sphere of gas, but around it, countless particles of ice and rock form brilliant, shimmering bands that stretch for hundreds of thousands of miles. From afar, they appear solid, but up close they are delicate, made of fragments ranging from dust grains to boulders the size of houses. Saturn itself is less dense than water. If a cosmic ocean existed, it would float. Its winds are fierce, its storms vast, yet its beauty lies in those fragile rings which reflect sunlight in a way no other planet can. To see Saturn through a telescope, even a small one, is to glimpse perfection, a reminder that the cosmos can be not only immense, but breathtakingly graceful. The mystery of Saturn's rings. But even in their beauty, the rings hold secrets. No one is certain exactly how they formed. Some believe they are remnants of a shattered moon, torn apart by Saturn's gravity. Others think they are primordial, leftovers from the early solar system. The rings are surprisingly young in cosmic terms, perhaps only a few 100 million years old, and they may not last forever. Saturn's gravity slowly pulls their material inward, causing icy particles to spiral down like gentle rain into the planet's atmosphere. One day, far in the future, the rings may vanish entirely, leaving Saturn bare. For now, though, they remain delicate, temporary, a cosmic masterpiece caught in a fleeting moment of time. Imagine standing on a moon like Enceladus, looking across the sky to see them arch overhead, a ribbon of light curving around the planet, fragile and immense all at once. Titan, Saturn's largest moon. At first glance, Titan looks like no other moon. It is cloaked in a thick golden haze that hides its surface from direct view. Beneath that veil lies a world both alien and strangely familiar. Titan is larger than the planet Mercury, and it is the only moon in the solar system with a dense atmosphere. That atmosphere is rich in nitrogen, like Earth's, but laced with methane, creating an environment utterly unlike our own. Yet within this alien chemistry lies something remarkable. Titan has rivers, lakes, and seas, not of water, but of liquid methane and ethane. Vast shorelines stretch across its surface, dunes ripple across deserts of icy grains, and rain falls from orange skies. To stand there would be to breathe poison, to freeze in bitter cold, but to witness a landscape eerily reminiscent of Earth. Titan whispers of possibility, of chemistry that may hint at life, not as we know it, but in forms we cannot yet imagine. Methane lakes on Titan. Imagine walking along a beach where the waves are not water, but liquid methane, lapping quietly against a frozen shore. Titan seas, like Kraken Mare and Ligeia Mare, are vast enough to rival our Great Lakes. Their surfaces may glisten in the dim light of a distant sun, reflecting the hazy sky. Rivers carve into the land, channels winding toward these lakes, carrying hydrocarbons instead of water. Methane on Titan cycles just as water does on Earth, evaporating, condensing, falling as rain, returning again. It is a mirror of our hydrological cycle, but with entirely different ingredients. Scientists wonder what chemistry might stir in those dark, cold seas. Could there be forms of life that thrive in liquid methane, building biology on rules we cannot yet fathom? Titan's lakes remind us that nature's imagination is far wider than our own, and that life, if it exists elsewhere, may not look like anything we expect. Enceladus, Saturn's icy moon with geysers. Now turn to another of Saturn's moons, smaller, brighter, and more surprising. Enceladus is a frozen world, its surface a shell of dazzling ice. Yet from cracks near its south pole, geysers erupt, shooting plumes of water vapor and ice crystals far into space. These fountains are so powerful that they feed material into Saturn's rings, replenishing them with fresh ice. Beneath Enceladus's crust, scientists believe, lies a global ocean kept warm by tidal forces from Saturn's pull. In that hidden sea, heated by hydrothermal vents, conditions may resemble the deep oceans of Earth, where life thrives in total darkness. The Cassini spacecraft flew through these plumes and detected organic molecules, salts, and hints of chemical reactions that could support biology. Enceladus, though small, has become one of the most promising places to search for life. To see its geysers against the backdrop of Saturn is to watch a frozen world breathing into space. Uranus, the tilted planet. Drifting farther outward, we come to Uranus, a planet that hides its strangeness behind a calm blue face. Its hue comes from methane in its atmosphere, absorbing red light and scattering blue. But the most curious feature of Uranus is its tilt. Unlike most planets, which spin upright or at a modest angle, Uranus rolls on its side, tilted more than 90 degrees. Its poles, rather than its equator, point almost directly toward the sun. Seasons on Uranus last for decades, with one hemisphere bathed in sunlight while the other is locked in darkness. Scientists believe a colossal collision long ago may have knocked Uranus over, leaving it forever skewed. This unusual tilt shapes not only its seasons but also the way its magnetic field twists and bends. Unlike any other planets, Uranus appears calm from afar, but beneath its turquoise glow lies a history written in violence and chance. Why Uranus rotates on its side. Let's go deeper into the mystery. How did Uranus come to be so oddly positioned? The leading theory suggests that in the early solar system, when worlds were still colliding and forming. Uranus was struck by a massive object, perhaps even multiple impacts, that toppled it onto its side. Another possibility is that the pull of nearby giant planets gradually destabilized its spin, nudging it into this unusual state. Whatever the cause, the result is a planet unlike any other. Imagine living there. A day lasts about 17 hours, but the sun's path across the sky would be bizarre. Sometimes circling overhead, sometimes refusing to rise at all for years. The tilt creates extremes that challenge our earthbound notions of time and light. Uranus is a reminder that even the largest planets are vulnerable to cosmic accidents, and that the solar system's order was shaped by chance as much as by gravity. The faint rings of Uranus. At first glance, Uranus may appear serene, its pale blue hue unbroken by visible adornments. Yet in 1977, astronomers discovered that it is encircled by a system of rings, far fainter and narrower than Saturn's spectacular bands. These rings are composed of dark particles, some no larger than dust grains, others stretching several meters across. Unlike Saturn's icy splendor, Uranus's rings absorb most of the light, appearing as ghostly silhouettes against the planet's glow. Their origin remains uncertain. Some may be remnants of a shattered moon, torn apart by tidal forces. Others may have formed from material left over from Uranus's formation, trapped in its gravitational pull. To imagine standing on one of its moons, looking up at these faint, delicate rings, arching across the sky, is to witness subtlety on a grand scale. They are quiet structures, almost invisible, yet they speak volumes about the hidden complexity of the planet they encircle. Neptune, the windy planet. Drifting still farther into the solar system, we encounter Neptune, a world of brilliant cobalt, sculpted by storms and high-speed winds. It is the windiest planet in our neighborhood, with gusts reaching over 1,200 miles per hour, faster than the strongest hurricanes on Earth. Its atmosphere is composed of hydrogen, helium, and methane, giving it that intense blue color. White clouds drift across the sky, often in long, fast-moving streaks. Though it is the farthest planet from the Sun, Neptune is far from static. Giant storms can appear and vanish, and the Great Dark Spot, once observed by Voyager 2, showed how dynamic its weather can be. Imagine standing on its frozen cloud tops, though no human could survive the winds and crushing pressures, watching storms that dwarf the size of continents rage endlessly. Neptune is a planet of motion, a reminder that even in the deep, dark reaches of the solar system, energy and change never cease. The speed of Neptune's storms. Here's something astonishing. The storms on Neptune are not only massive, they move at extraordinary speeds. Winds can whip around the planet faster than the sound of a bullet, carrying clouds and vortices across the globe in mere days. These storms are fueled not by the sun, which provides only a faint glow at Neptune's distance, but by heat rising from the planet's interior. Despite the deep cold, the planet radiates more energy than it receives, and this internal warmth drives convection, creating dynamic weather unlike anything on Earth. Cyclones and anticyclones churn in its atmosphere, sometimes merging, sometimes fading, leaving patterns that are ever-changing. Observing Neptune is to witness chaos on a planetary scale, where invisible currents of heat and pressure sculpt clouds into fleeting masterpieces, constantly reminding us of the energy that still flows in the farthest reaches of our solar system. Triton, Neptune's captured moon. Now let us turn to Triton, Neptune's largest moon and one of the most unusual in the solar system. Unlike other large moons, Triton orbits backward, a clue that it was likely captured rather than formed alongside Neptune. Its surface is a frozen expanse of nitrogen ice, punctuated by geysers that spout plumes into the thin atmosphere. These geysers are thought to be powered by seasonal heating, creating jets that rise tens of miles above the surface. Triton's orbit is slowly decaying. Over millions of years it may spiral inward, eventually breaking apart or colliding with Neptune. Imagine standing on its icy surface, looking up at the immense deep blue planet around which it circles backward, while plumes of nitrogen vapor erupt in the distance. Triton is a frozen world in motion, a captured wanderer that carries the history of cosmic migration and the ongoing story of planetary change. The dwarf planet Pluto. Finally, we reach the outer edge, to a small, distant world that once held the title of ninth planet. Pluto is a cold, icy sphere, only 2/3 the size of our moon, yet it has long captured our imagination. Its surface is a patchwork of plains, mountains, and icy deposits, glowing faintly in the dim sunlight of the outer solar system. Pluto's atmosphere, tenuous and ever-changing, expands when it nears the sun and collapses as it retreats into the depths of its orbit. Once considered the ninth planet, Pluto was reclassified as a dwarf planet in 2006. Yet this small world remains profoundly important. It teaches us that size is not the only measure of significance, and that even distant frozen bodies can hold deep scientific mysteries. From its heart-shaped ice plains to its complex geology, Pluto is a reminder that the solar system's edge is not barren, but full of life. If not biological, then geological and chemical, shaping worlds in silence. Pluto's eccentric orbit. At first glance, Pluto's journey around the Sun seems ordinary, a distant ellipse tracing centuries-long paths through space. Yet its orbit is unusual, tilted and elongated, crossing the path of Neptune at times. Unlike the near-circular orbits of most planets, Pluto swings far out into the Kuiper belt, then arcs closer in, completing a single orbit every 248 Earth years. For part of its orbit, it is closer to the Sun than Neptune, a reminder that the solar system is not static, but full of dynamic motion. This eccentricity challenges our sense of order, revealing the subtle gravitational dances that have shaped its path. Pluto is small, cold, and distant, yet its orbit tells a story of migration, encounters, and cosmic choreography spanning billions of years. To imagine standing on its frozen surface, watching the sun appear as a bright star rather than a warm orb, is to feel the vast scales of time and distance that govern the outer solar system. Pluto's heart-shaped ice plain. Here's something remarkable. One of Pluto's most famous features is the heart-shaped plain known as Tumba Regio. From the vantage of spacecraft like New Horizons, it stretches across hundreds of miles, a vast expanse of nitrogen ice with smooth, undisturbed plains and subtle ridges. The heart is not just visually striking, it is geologically active. Evidence suggests glaciers flow slowly across its surface, shifting ice and reshaping the landscape over millennia. Even in a world so cold, processes of change continue, quietly moving mountains of ice and creating textures that tell a story of internal heat and surface renewal. The heart's gentle shape seems almost poetic, as if the planet itself were offering a symbol of life and curiosity to those studying it from afar. In that frozen expanse, we see a planet small in size, yet immense in wonder, a reminder that even the tiniest worlds hold grandeur. Charon. Pluto's large moon. Think about companionship in space. Pluto is not alone. It has a large moon, Charon, so massive relative to Pluto that the two bodies almost orbit a common center of gravity, like partners dancing around a shared point. Charon is covered in cliffs, canyons, and icy plains, revealing a surface that has cracked and shifted over time. It lacks a thick atmosphere, leaving the landscape exposed to cosmic radiation and the endless dark. The Pluto-Charon system is unique, a binary world unlike any other in the solar system, where the two bodies circle each other in a gravitational embrace that is both delicate and precise. Observing Charon from Pluto would be like seeing a world fill much of your sky, a silent companion, frozen yet intimate, sharing its orbit across the void. Their interaction is a reminder that even in the outer reaches, celestial bodies do not drift alone, they form relationships that shape their destinies. Other dwarf planets, Eris, Haumea, and Makemake. Beyond Pluto lies a frozen frontier of small, icy worlds, each with its own story. Eris, slightly smaller than Pluto, is dense and distant, moving slowly through the darkness of the scattered disk. Haumea, with its elongated shape and rapid spin, challenges our understanding of what a planet can be, rotating so quickly that it bulges outward at the equator. Makemake, another icy body, shines faintly, a solitary traveler in a distant orbit around the Sun. These dwarf planets, once unseen and ignored, now remind us that the solar system is far larger and more diverse than our early models suggested. They are fragments of formation, preserved in ice and rock, carrying clues about the chaotic processes that shaped our neighborhood billions of years ago. Each of them is a whisper of the solar system's past, a frozen sentinel at the edge of our vision, silently marking the boundary between known and unknown. The Kuiper Belt, a frozen frontier. Let us pause to look outward. Beyond Neptune stretches the Kuiper Belt, a vast ring of icy bodies, remnants of the early solar system. It is a frozen frontier, home to thousands, perhaps millions of small objects, rock and ice, some as tiny as pebbles, others comparable to Pluto. These bodies orbit the sun slowly, in a quiet dance that has persisted for billions of years. The Kuiper Belt is a place of preservation, where ancient material remains largely unchanged, offering a window into the conditions and processes of the early solar system. Comets occasionally wander inward from this region, bringing with them material unaltered since the dawn of our cosmic neighborhood. To imagine drifting through the Kuiper Belt is to feel the vastness and silence of space, where time stretches almost infinitely, and the remnants of creation float untouched, like a frozen museum of the solar system's infancy. The scattered disk beyond Neptune. At first glance, the scattered disk seems almost an afterthought, a distant extension of the Kuiper Belt, yet it is a region of extremes, populated by icy worlds that venture far from the sun, in elongated orbits that swing them deep into the darkness of space. Objects here, such as Eris and other distant dwarf planets, experience temperatures barely above absolute zero and periods of sunlight measured in centuries. Their paths are shaped by the gravitational nudges of Neptune and the residual chaos of the early solar system. To imagine these icy wanderers is to imagine time stretching almost beyond comprehension, with years lasting centuries and millennia passing in quiet solitude. The scattered disk is a frontier of mystery, a repository of primordial material, holding clues to how planets migrated, collided, and settled into the delicate structure we see today. It reminds us that the solar system does not end with Neptune, but continues into a vast frozen hinterland. Comets, icy visitors from deep space. Here's something enchanting. Comets are travelers from the fringes of the solar system, icy bodies that carry whispers of its earliest days. Most spend millennia in distant orbits, frozen and dark, until a gravitational nudge sends them inward. As they approach the sun, they awaken. Ice sublimates, forming luminous tails that stretch millions of miles, pointing away from the sun like celestial brushes across a black canvas. Comets are ephemeral, beautiful, and unpredictable. Each tail is a mix of gas and dust, sculpted by solar winds and radiation, glowing softly in the cold light. Ancient civilizations watched these visitors with awe and trepidation, seeing omens in their sudden appearances. Modern astronomers study them for science, finding organic molecules and clues to the primordial chemistry that may have seeded life on Earth. A comet is both messenger and memory, a frozen fragment carrying the story of the solar system across eons of silence. The Oort cloud, a distant shell of comets. Imagine a halo surrounding the solar system, stretching nearly a light year from the sun, composed of trillions of icy bodies. This is the Oort cloud, a distant shell of comets that forms the outermost boundary of our star's influence. It is invisible, yet vast, a quiet reservoir of ancient material. Gravitational tugs from passing stars or galactic tides can send some of these comets inward, turning them into the bright, transient visitors we occasionally witness from Earth. The Oort cloud is a reminder of scale. The solar system is not merely the planets and moons we see in the night sky, but an immense structure extending far beyond the orbit of Pluto or even the Kuiper Belt. To consider its size is to confront the vastness of our cosmic neighborhood and the fragility of human perception. The Oort cloud is a quiet, frozen testament to the beginnings of our star system, a repository of untouched history at the edge of our reach. How comets grow tails near the sun. Think of a comet hurtling toward the sun. At first, it is little more than a cold, dark rock, invisible against the black backdrop of space. But as sunlight warms its icy surface, gases escape, carrying dust along with them. This process forms the coma, a glowing cloud surrounding the nucleus, and the tail, which can stretch for millions of miles. The tail always points away from the sun, shaped by the solar wind, a delicate dance between light, gravity, and particles. Some comets have multiple tails, one composed of gas, another of dust, and they can curve, twist, and shimmer, creating celestial displays visible even from Earth. Each passing comet is ephemeral, a fleeting reminder of the solar system's dynamism, born at its edge and brought into fleeting proximity with our eyes. Comets show us that even in deep space, activity and transformation continue, a cosmic performance that lasts for weeks or months before fading again into darkness. Asteroids, rocky leftovers of formation. Finally, let us pause on asteroids, the rocky fragments left behind after planets formed. These small bodies, primarily found between Mars and Jupiter, are relics of a chaotic era when the solar system was young and collisions were common. Some are jagged and cratered, others smooth from eons of slow motion. Their compositions vary. Some are metallic, others rocky, and some contain carbon-rich compounds. They orbit in predictable paths. Yet even here, gravitational nudges from planets or collisions can send one spiraling inward toward the sun. Many asteroids are ancient, unchanged for billions of years, offering glimpses of the material from which Earth, Mars, and Jupiter itself coalesced. To study an asteroid is to hold a fragment of creation, a miniature fossil of the processes that built the planets, silent witnesses to cosmic history. The asteroid belt between Mars and Jupiter. At first glance, the region between Mars and Jupiter might seem empty, a void in the solar system. Yet here lies the asteroid belt, a vast collection of rocky fragments and minor worlds orbiting the Sun. These objects range from tiny pebbles to dwarf planets like Ceres, forming a kind of cosmic rubble field. They are remnants of the early solar system, material that never coalesced into a full-size planet, perhaps because Jupiter's immense gravity prevented them from combining. The belt is not densely packed as often imagined. Spacecraft can navigate through it safely, yet it contains a record of billions of years of collisions, heating, and orbital changes. Each asteroid carries a story of violent impacts, melting and cooling, and the slow erosion of surfaces. To imagine drifting through the asteroid belt is to see the debris of creation itself, floating silently in the sunlight. Fragments of a time before Earth even existed. The dwarf planet Ceres. Among the asteroids, one world stands out, Ceres, the largest object in the asteroid belt, and a dwarf planet in its own right. Its surface is a mixture of rock and ice, pockmarked with craters, yet also marked by smooth plains and mysterious bright spots. These bright regions, first glimpsed by telescopes and later studied closely by the Dawn spacecraft, are composed of salts left behind by briny water, seeping from below. Ceres may even harbor pockets of liquid water beneath its crust, making it a tantalizing candidate in the search for life or prebiotic chemistry. Though it is small, about a third of the Moon's diameter, Ceres is a world of contrasts, frozen yet geologically active, ancient yet still evolving. It reminds us that even in the asteroid belt, where worlds seem minor and inert, there are stories of internal energy, movement, and subtle transformation. Why some asteroids are metallic. Think about the diversity within the asteroid belt. While many are rocky or carbon-rich, some are composed largely of metals, iron, nickel, and other elements. These metallic asteroids are thought to be fragments of larger parent bodies that were once molten and differentiated, separating dense cores from lighter crusts. When these bodies shattered in collisions, the cores were exposed, floating through space as relics of ancient processes. These metallic asteroids are time capsules of the solar system's interior, preserving materials that otherwise might remain hidden deep within planets. Imagine holding one in your mind, a chunk of iron, hundreds of millions of years old, a fragment of a world that no longer exists except in pieces. Such asteroids reveal the invisible architecture of planetary formation, showing us that even in destruction, there is knowledge waiting to be discovered. Meteoroids, meteors, and meteorites. Here's something closer to home. Small fragments of rock and metal, called meteoroids, drift through space, remnants of asteroids or comets. When one enters Earth's atmosphere, friction ignites it into a streak of light, a meteor or shooting star, burning bright across the night sky. If any part survives and reaches the surface, it becomes a meteorite, a tangible piece of the cosmos we can hold in our hands. Meteorites are ancient, often billions of years old, carrying clues about the materials and processes that formed the planets. Every meteor streaking overhead is a reminder that the solar system is not distant and static. It touches us, depositing fragments of other worlds onto our own. In a quiet night sky, Watching meteors fall, we are witnessing an ongoing dialogue between Earth and the wider cosmos. How impacts have shaped Earth. Finally, consider the role of cosmic collisions in shaping our own world. Asteroids and comets have struck Earth countless times, sculpting landscapes, forming craters, and even influencing the course of life. Some impacts caused mass extinctions, wiping out species and making way for new ones to evolve. Others delivered water and organic molecules, seeding the ingredients for life itself. The Moon may even be a product of one such cataclysmic collision. In this way, Earth's story is inseparable from the larger solar system, its surface and life molded by the same forces that created and shaped the planets around it. Impacts are not merely destructive, they are creative, shaping worlds over eons in ways both subtle and profound. To look at the craters on Earth, or to imagine the fireballs streaking across the sky, is to see our planet as part of an ongoing cosmic ballet where chance and gravity choreograph creation and change. The role of Jupiter in protecting Earth. At first glance, Jupiter may seem a distant, indifferent giant, swirling quietly in the outer solar system, yet its gravity plays a crucial role in shielding Earth. By sweeping up or redirecting comets and asteroids that might otherwise collide with our planet, Jupiter acts as a cosmic guardian. Its immense mass alters trajectories, capturing or flinging potential hazards outward into the depths of space. Some scientists call it the solar system's vacuum cleaner, though it is far more elegant than a mere mechanical analogy. Without Jupiter's presence, Earth's history might have been very different. Impacts could have been more frequent, life potentially snuffed out before it ever took hold. Observing Jupiter reminds us that stability in the solar system is not automatic. It is shaped by the interactions of massive bodies over billions of years. Our planet's safety, in a very real sense, is bound to the movements of a world so far away, yet so influential. The concept of planetary migration. Here's something surprising. The planets we see today may not be where they formed. In the early solar system, gas giants and smaller worlds did not sit quietly in their orbits. They moved, sometimes dramatically, shifting positions as they interacted gravitationally with one another and with surrounding material. This process, known as planetary migration, explains many of the puzzling features we observe today. Why Jupiter and Saturn occupy the orbits they do, why Uranus and Neptune ended up far from the Sun, and why small bodies like Pluto and the Kuiper Belt objects are scattered across the outer solar system. Migration is slow yet powerful, a subtle reshaping of the cosmic neighborhood, reminding us that the solar system is not frozen in place, but a dynamic, ever-changing environment. It is a story of movement and adjustment, of gravity sculpting a family of worlds over billions of years. Why Uranus and Neptune may have moved outward. Let us consider Uranus and Neptune. Evidence suggests these ice giants did not always reside at the edges of the solar system. Early models indicate they formed closer to the Sun and later migrated outward, pushed by gravitational interactions with Jupiter, Saturn, and the remaining disk of material. This outward movement may have scattered smaller objects into the Kuiper Belt and the scattered disk, creating the frozen frontier we see today. Such migration may have stabilized the orbits of the inner planets, allowing Earth to remain in a relatively calm zone conducive to life. Imagine billions of years ago, Uranus and Neptune moving through space, shifting positions imperceptibly, yet dramatically influencing the arrangement of countless other bodies. This celestial choreography shaped the solar system's architecture, highlighting that even the largest planets are not fixed, but participants in a grand gravitational dance. The puzzle of the Sun's rotation. At first glance, the Sun may seem eternal, a calm, glowing sphere at the center of our solar system. Yet beneath its serene appearance lies a puzzle. The Sun does not rotate as a solid object. Its equator spins faster than its poles, completing a rotation in about 25 days, while the poles take more than 30. This differential rotation creates twists and tangles in the Sun's magnetic field, which in turn drives sunspots, solar flares, and other dynamic activity. Understanding why the Sun rotates this way requires looking deep into its fluid interior, where layers of plasma and convection currents interact over immense scales. This motion is crucial to life on Earth. It drives the solar cycles that influence our climate and space weather. The Sun is not static. It is a living, moving entity, its rotation shaping the very environment in which the planets orbit and life thrives. Sunspots and solar cycles. Here's something fascinating to contemplate. Sunspots, the dark blotches that appear on the sun's surface, are manifestations of intense magnetic activity. They come and go, waxing and waning in roughly 11-year cycles. When sunspot activity peaks, the sun's surface becomes more turbulent, emitting more solar radiation and sometimes stronger solar storms. During periods of low activity, Earth experiences calmer solar conditions. These cycles are not merely curiosities, they influence Earth's upper atmosphere, the auroras, and even climate patterns over long timescales. Observing sunspots is like watching the heartbeat of our star, a rhythm both predictable and surprising, connecting our daily lives to the subtle, immense forces at work hundreds of millions of miles away. They remind us that the sun is not a uniform sphere, but a dynamic, ever-changing source of energy and life. Solar flares and coronal mass ejections. Think about the sun, not as a calm orb, but as a boiling, roiling sphere of plasma, its surface alive with energy. Sometimes, magnetic field lines twist and snap, releasing immense bursts of energy in the form of solar flares. These flares can be accompanied by coronal mass ejections, huge clouds of charged particles hurled into space at millions of miles per hour. When directed toward Earth, these events can disrupt satellites, power grids, and radio communications. But they also create breathtaking auroras that shimmer across polar skies. Solar flares are reminders of the sun's immense power, a visible expression of the magnetic energy flowing within, even from millions of miles away. We can feel their presence, whether through dazzling lights in the sky or subtle disturbances in Earth's magnetic environment. They show us that our star is not passive. It is dynamic, dramatic, and intimately connected to the planets that orbit it, the solar wind and its effect on Earth. Here's something subtle yet profound. The sun constantly emits a stream of charged particles, known as the solar wind, that flows outward in all directions. These particles interact with Earth's magnetic field, shaping the magnetosphere and occasionally triggering the glowing curtains of the auroras. The solar wind can erode atmospheres of smaller planets or moons that lack magnetic shields, but Earth's magnetic field and atmosphere protect us. It also shapes the heliosphere, a vast bubble encompassing the solar system, extending far beyond the orbit of Pluto. Without the solar wind, our understanding of space weather, auroras, and even the behavior of comets would be entirely different. It is a quiet, constant reminder that the sun's influence reaches far beyond its visible light, touching every planet, moon, and asteroid with invisible streams of energy that shape their surfaces, atmospheres, and magnetic environments. The heliosphere, the sun's invisible bubble. Imagine an immense invisible bubble surrounding the sun, extending billions of miles into space. This is the heliosphere, formed by the interaction between the solar wind and the interstellar medium. It acts as a protective cocoon, deflecting much of the cosmic radiation that would otherwise flood the inner solar system. The heliosphere is not static. It pulses and shifts in response to solar activity, expanding and contracting over time. Its outer boundary, the heliopause, marks the edge of the sun's influence and the beginning of interstellar space. To traverse this invisible barrier is to leave the familiar warmth of the sun and enter the vast unknown, where distances and conditions defy human comprehension. The heliosphere is both shield and signature, a measure of our star's reach and the subtle, silent forces that protect the planets within its embrace. Voyager spacecraft leaving the solar system. Now let us consider human ambition in the vastness of space. Launched in 1977, the Voyager spacecraft were tasked with exploring the outer planets, yet their journey continues far beyond. Voyager 1 and 2 have crossed the boundaries of the heliosphere, entering interstellar space. They carry with them the first human-made objects to leave the protective bubble of the sun, tiny ambassadors into the void. On board are the famous golden records, containing sounds and images representing life on Earth, our attempt to communicate across light years and time. Voyager reminds us that exploration is not confined to the planets we orbit, but extends into the cosmic wilderness. Their journey is both scientific and poetic. Instruments collecting data, cameras capturing glimpses of distant worlds, and human ingenuity reaching outward into the darkness. propelled by curiosity and courage. Pioneer plaques and their message. Before Voyager, the Pioneer spacecraft carried their own message into the cosmos. Plaques etched with diagrams representing humanity and Earth's location in the galaxy. The plaques are remarkably simple, yet profoundly hopeful, containing images of a human male and female, a map of our solar neighborhood, and symbols describing our units of measurement. They are intended not for us, but for any civilization that might encounter them, millions or billions of years hence. In sending these messages, humanity acknowledged that we are a small species on a small planet, yet capable of thinking, dreaming, and reaching outward. The plaques are a quiet testament to our curiosity, a reflection of hope, and an invitation for connection that transcends time and space. They symbolize our desire to leave a mark, however modest, in the vastness of the universe. The edge of the solar system. At first glance, the solar system may seem to end with Neptune, or perhaps Pluto, but in truth, its boundaries extend far beyond the planets we know. The edge is a gradual, hazy transition, where the sun's gravitational grip weakens and interstellar space begins to take over. It is marked by the outer reaches of the Kuiper Belt, the scattered disk, and finally, the distant Oort cloud, where icy bodies drift silently in near-eternal darkness. The sun's influence, carried by the solar wind, fades over billions of miles, until the heliosphere itself gives way to the galaxy's interstellar medium. Beyond this frontier, there is no clear horizon, only the faint tug of distant stars and the whispers of cosmic history. The solar system's edge reminds us of scale, how vast even our star's reach is, and how small our world is in comparison. It is a quiet, almost poetic boundary, separating the familiar warmth of the sun from the cold mystery beyond, how long it takes sunlight to reach Earth. Here's a gentle thought. The light that warms us and makes life possible does not arrive instantaneously. Sunlight takes roughly 8 minutes and 20 seconds to travel the 93 million miles from the sun to Earth. In that short span, photons born in the sun's core have already endured a journey of hundreds of thousands of years inside the solar plasma, wandering randomly through dense layers before escaping into space. When we see the sun rise or set, we are witnessing a moment that began long ago, a fusion of energy and time. This delay, though brief on cosmic scales, connects us intimately with processes occurring far beyond our planet. Each ray of sunlight carries history, energy, and life, reminding us that even light, a symbol of immediacy, is a traveler across space and time, linking our daily experience to the heart of a star. The changing definition of planets. Think about how definitions can shift, even in science. For centuries, Pluto was called the ninth planet, a status later challenged by discoveries of similar-sized bodies in the outer solar system. In 2006, the International Astronomical Union introduced a refined definition of planets, requiring them to clear their orbit of other debris. Pluto, along with Eris, Haumea, and Makemake, was reclassified as a dwarf planet. This change sparked debates, nostalgia, and new curiosity. But it also reflected a deeper understanding. The solar system is diverse, and the distinctions we draw are as much about clarity as they are about reality. Categories evolve as knowledge grows. Reclassification does not diminish Pluto's wonder. It invites us to see it within a broader context, among many small worlds that share its icy, distant realm. It is a lesson that science is dynamic, and discovery often reshapes what we thought we knew. How many moons are in the solar system? At first glance, moons might seem like minor companions, but the solar system hosts over 200 confirmed natural satellites, and more are likely awaiting discovery. Some are massive, like Ganymede or Titan, rivaling planets in size. Others are tiny, irregular fragments captured by gravity or debris from collisions. Moons orbit every kind of planet, rocky, gaseous, and icy alike, each forming unique relationships with their host. Some, like Io, are geologically violent, with constant volcanic activity. Others, like Europa or Enceladus, conceal oceans beneath icy crusts. They influence tides, stabilize rotation, and even shape atmospheres. To count moons is to understand the solar system's complexity. the subtle gravitational dances that maintain order. Each moon is a miniature world, offering a glimpse into the diversity of planetary environments and the intricate connections that make our cosmic neighborhood so fascinating. Rings beyond Saturn: Uranus, Neptune, and Jupiter. Here's something surprising. While Saturn's rings are the most spectacular, rings are not unique to it. Jupiter, Uranus, and Neptune also host ring systems. Though fainter and less massive, Jupiter's rings are dark and thin, made mostly of dust from its moons. Uranus's rings are narrow and well-defined, while Neptune's are faint and contain arcs of clumped material, perhaps held together by unseen moons. These rings reveal that even smaller particles can organize into elegant structures under the influence of gravity. They also tell a story of collisions, disintegration, and continuous evolution, as dust and ice move and interact over millions of years. To look at these rings is to see patterns emerge from chaos, subtle harmonies that persist even at the outer edges of the solar system, demonstrating that beauty and structure exist even where the sun's light is faint and the planets distant. Why Pluto was reclassified as a dwarf planet. At first glance, the story of Pluto's reclassification may seem simple, a matter of naming, yet it reflects a profound evolution in our understanding of the solar system. For decades, Pluto was counted as the ninth planet, a distant companion, quietly orbiting beyond Neptune. Then came discoveries of similar bodies in the Kuiper belt, each icy and remote, some even larger than Pluto. Astronomers realized that if Pluto remained a planet, the definition would become unwieldy. In 2006, the International Astronomical Union established criteria. A planet must orbit the Sun, be spherical, and clear its orbit of other debris. Pluto met the first two, but not the third. Reclassified as a dwarf planet, Pluto's status changed, yet its fascination did not diminish. This moment in scientific history reminds us that knowledge evolves. Even a world once firmly established in our minds can shift in meaning, as new discoveries illuminate the complexity of the cosmos. The search for Planet 9. Imagine a massive, unseen world lurking in the dark, reaches beyond Neptune. Astronomers have observed unusual clustering in the orbits of distant Kuiper belt objects, hinting that a large planet, nicknamed Planet 9, may exist far from the Sun. Its presence has not yet been confirmed, but its gravitational influence could explain anomalies in the outer solar system. Planet 9, if real, would be a cold, distant giant, invisible to the naked eye, silently shaping the orbits of icy bodies over billions of years. The search for it combines meticulous observation, orbital modeling, and patient exploration, a modern detective story on a cosmic scale. It reminds us that the solar system is not fully mapped, that mysteries remain, and that even today, new worlds may be waiting to reveal themselves beyond the familiar planets we know so well. Exoplanets compared to our solar system. Let us step outside our neighborhood entirely to the thousands of exoplanets discovered orbiting distant stars. These worlds reveal a staggering variety: gas giants skimming close to their suns, rocky super-Earths, planets in multi-star systems, and worlds unlike anything in our own solar system. Some orbit in predictable, stable patterns. Others follow eccentric, tilted, or even retrograde paths. By comparing these exoplanets to our familiar planets, we gain perspective on our own system's uniqueness. Our solar system is orderly, with small rocky planets inside and gas and ice giants outside, a configuration that may be rare. Exoplanets teach us that planetary formation is diverse and often chaotic, and that our understanding of normal is always expanding, challenged by discoveries from across the galaxy. Why Earth may be rare among planets. Here's a humbling thought. Among the countless planets orbiting other stars, Earth appears remarkably special. Its combination of liquid water, a stable atmosphere, protective magnetic field, and moderate climate may be rare in the universe. It resides in the habitable zone, yet this alone is insufficient. It also benefits from Jupiter's shielding influence, a moon that stabilizes its tilt, and a long period of geological and biological stability. These factors, finely tuned over billions of years, create conditions for life as we know it. Earth's rarity is both fragile and precious, a reminder of the delicate balance required for life to thrive. It invites reflection on our responsibility as stewards of this unique world, suspended in space amid countless other planets, many lifeless, some still unexplored. the solar system as a tiny part of the galaxy. Finally, let us zoom out to the grandest scale. The solar system, vast as it may seem, is but a tiny part of the Milky Way galaxy, itself a collection of hundreds of billions of stars. Each star may host its own planets, moons, and rings, its own comets and icy edges. The Sun and its companions orbit the galactic center, circling every 225 million years, while stars pass near and far in a cosmic dance. Our solar system is a microcosm, a family of worlds spinning in a tiny corner of a spiral arm, connected yet small, illuminated yet dwarfed by the vastness around it. To see it this way is both humbling and beautiful. We are small, yet we observe, understand, and wonder. And in that act of curiosity, we connect with the universe itself, tracing the intricate patterns of motion, light, and time across the infinite canvas of space.